welcome everyone. And this is our, I think, first talk of this semester. So Professor Huse, thank you so much for agreeing to give your talk. And yeah, the floor is yours.
Okay, so I'm gonna tell you about a particular project I did together with Professor Bacher's lab. So this is atoms. That's it. Optical lattice. Say more what I mean. And so the key people here were, any of you guys ever met Elmer? He's graduated and gone to Harvard. So he was the lead student in the laboratory. And then my student, Alan Morningstar, who's still here, he will, so these are graduate students. Alan will graduate this summer. Perhaps some of you might have had him as an AI, I'm not sure, and various other people, and of course, Professor Bacher. And this actually came about by Alan convincing Professor Bacher's students that this would be something interesting to look into for reasons different than what happened in the end. They did the experiment, got data different from what Alan was looking for, and then we had to figure out what happened. And so we sort of made a nice discovery. So it was a nice project that way. We actually found something new rather than just confirming some idea we already had. Okay. So atoms in an optical lattice. I'm just going to talk about some basic stuff. I hope it's not too basic for too many of you, but you are undergraduates. I understand. Right. So these are ultra cold atoms. They're nominally cold on the Kelvin scale, 10 to the -7 degrees Kelvin or something like that. And they set up a standing laser, basically a laser coming this way, one this way. They're coherent. It makes a standing wave. And this is where the intensity is minimal, and this is where this is a potential. So the atoms see this potential, and it's proportional to the intensity of the light. So this is where the light has, it's a standing wave, and so there's places where nothing's happening, there's no light, and that's here at the maximum, and this is where the light is at the highest intensity in the middle of the wave where it's really going up and down strongly. The electric fields are very strong. The electric fields polarize the atoms and lower their energy. So where the electric fields from the light are strongest, the atom has the lowest energy, and where the electric fields from the light are smallest, the atom has the higher energy. And so that's how you get this potential. And this is actually the wavelength of the light, right? So, because basically what's happening with the electric field here is it's a standing wave, so it's oscillating between this configuration, and then a half a period later it's in this configuration. Here, there's no electric field ever. Here, it's oscillating with a big value. And so this is a minimum of this potential. This is a minimum of this potential. This is a maximum. And that's why the potential has a wavelength that's half the wavelength of the light. So that's, and then this is a strong potential, and the atoms in this experiment were cooled. So in each well, they're in the ground state. So in the well near the bottom here, it's like a harmonic oscillator. It's just the minimum of something. And the atom can sit in the ground state energy. And then the first excited state will be up here, and the next excited state, etc. but the atoms were cooled down, so they're all in the ground state in each well, but the wells are all identical, and the atoms can tunnel through this barrier from one well to the next. And so that makes a band. And it's like electrons in a crystal, right? In a crystal, you have a periodic potential. It's not sinusoidal. This is sinusoidal. The potential that an electron sees in a crystal is not sinusoidal, but it is periodic because every unit cell of the crystal is the same. And then so the light field is playing the role of the atoms in the crystal, and the electron is playing the role of the atom. So these are lithium 6 atoms, isotope 6. The lithium 6 atoms are playing the role of the electron in this setup here, the analogy to electrons in crystals. And they are fermions. So lithium is element 3. So it has 3 electrons, 6 nucleons, which are protons and neutrons, total of 9 fermions. Well, you can all go all the way down to the quark, and this becomes 18 quarks, right? But 3 electrons, so it's 21 fermions in a lithium atom if you go all the way down to the quarks. And when you have an odd number of fermions, it's a fermion. So these are fermionic atoms. People also work with lithium 7, not in Bacher's lab, but in other places. That's a boson because it has an even number of fermions. Okay, so that's right now. Right, so now the atoms are in these ground states and they're tunneling and they have a wave function. And so atoms with momentum P is a momentum, which is h bar k. K is a wave number, Planck's constant, have wave function psi going is ikx, right? And in a lattice like this, this is a function not of x as a continuous variable, but x is just 0, 1, 2, 3 sites, right? And so this is not we don't think of this as a function of x, with x being a real variable. It's a function of x, where x being an integer multiple of the lattice space, right? So this changes by e to the ika. So let's call A the lattice spacing. That's what we usually do. And A happens to be half the wavelength of the light that made up this optical lattice. So this changes by a factor of e to the ika from one site to the next, right? And we should think of it as having a value here and a value here, but no value in between, right? And so the most it can change is when this is -1, which corresponds to k equals plus or minus pi over a. So that's the highest momentum a particle in a lattice can have. It just can't have if it's only in the lattice and it doesn't really exist between the sites, it just can't have a higher momentum than plus or minus pi over a, or right. So it means P is the momentum P is only defined modulo 2 pi h bar over a. And there's a basic fact about particles in bands and crystals, okay, which some of you may have heard before, but I just want to make sure everybody is aware of that. And it's basically, the reason is the wave function looks like this, and the most you can change a unit magnet, the farthest you can get a unit magnitude, the complex number away from 1 is -1. That's just the farthest you can get away from 1. Right? And that corresponds to the highest possible momentum. Okay? And then, so somebody just- another board here, so some room. So the momentum range is the so-called Brougham zone, which runs from minus pi h bar over a to plus pi h bar over a. And this momentum, so here's momentum 0. This momentum is the same as that momentum, right? Because the thing that's, the momentum is really e to the IKA, right? That's the number, right? And this gives -1 and this gives -. So it's really the same. So the momentum really is only defined that way. Now, when you have a particle in a band like that tunneling through, we have an energy. So first I'm going to plot the energy as a function of the momentum, and it has a band, has a dispersion relation, which will look like this basically. Not a sine function, but qualitatively like that. And it has to have a smooth maximum here because it's really a function. This is really a cylinder, right? I flattened it out, but this point is the same as this point. We should think of P as existing on a circle, right? Which is the unit circle of those complex numbers. Okay. And then the velocity of a particle with a dispersion relation is V equals d dt. This is general, doesn't require quantum mechanics. Right. Okay. So if we plot the velocity as a function of P and put 0 here, here's when the momentum is positive, the velocity is positive. So that's kind of what you expect. Okay. But it goes back to 0. When the momentum reaches its maximum possible value, the velocity is 0. And that's a little different than you learned in freshman physics. And so the velocity looks like that. Right? Near 0 momentum, this is quadratic. We can call it p squared over 2m. And the velocity is p over m. But it's only valid at small p, and the velocity has a different behavior. Right? And so this is what happens with So of course at 0 momentum you have 0 velocity, but you also have zero velocity when the momentum is at its maximum possible value. Okay. Now let's apply a force. So when I say tilted optical lattice, what we're going to do is we're going to apply a uniform force along the x direction, which we can think of as just adding a potential that's a tilted potential, right? And so that's what I mean by tilted optical lattice. But let's add a force. Actually, I should pause. Anybody want to ask anything? Everybody's, yeah.
Okay, I was just going to quickly ask. Maybe you mentioned it, but why is the velocity 0 at the highest momentum there?
Because the velocity is given by the derivative of the energy with respect to momentum. This is one of Hamilton's equation of motion, and it's also true in Schrodinger's equation. We're making a wave. This is there's a discussion about making wave packets and how they propagate in the lattice, which is a little complicated, but it's this. And so since the energy as a function of momentum is flat at the here, right? This is supposed to be flat. Its derivative is 0, and that's so velocity is 0. So we're going to add a force F going in, say, this direction. F. And now we can just use, once we've accepted that our particle has this energy as a function of momentum, as well as this momentum, which is only defined modulo 2 pi over h bar. That's coming from quantum mechanics. Once we add the force, we can just do classical mechanics. So we're going to do Newton's law, but we're going to do the correct Newton's law, which is F equals dp dt, right? Which is only F equals ma if the energy is a quadratic function of p, but here it isn't, right? So F equals ma is, but that's, even in special relativity, you throw out F equals ma and you use F equals dp dt. So we have to use F equals dp dt, but it's a constant force, uniform force. So P is just going to be F times T. It's just going to, the momentum is just going to, it's a constant force, constant, quote, acceleration. But by acceleration, I mean time derivative of the momentum, not time derivative of the velocity, right? And so P just grows linearly, right? And so what happens is if you put a particle in a wave packet and say it's here in the band, it just goes, it goes around, right? And this is the same as this point. So it never leaves this place, but it's always going that way along this curve. It's going to higher momentum. It's always going to higher momentum, but because the momentum is on a circle, it just keeps doing the same thing over and over again, right? And when it's over here, it has a positive velocity. And when it's over here, it has a negative velocity. But the average velocity over the whole thing has to be 0 because the velocity is just the gradient of this periodic function. So you put a constant force on it, the momentum steadily increases, but the position and the velocity just oscillate. And this is what's called Bloch oscillations, after Felix Bloch, so Bloch oscillations. And once quantum mechanics was formulated, people realized that this is the solution for a particle in a band. It happens that for electrons in crystals, you can't really see this because you can't get the force strong enough. So an electron in a crystal, it'll always scatter at some point, right? And you can't get a full Bloch oscillation and see the oscillation before it scatters. So they were never really seen in electrons in crystals. I think maybe very recently people have gotten into that regime. But when you do these ultra cold atoms, it's just like it happens very easily, right? Okay, but let me give you another picture of this. So this is the band. So this is the particle in the lowest state in each well, and it's able to tunnel from one well to the other, and that's its kinetic energy. So its kinetic energy is the energy of tunneling from one well to the other. And that energy, that can give it a total energy, which is in this interval here, right? When it's at 0 momentum, it has an energy down here. When it's at highest momentum, it has an energy down here. So there's this energy range, which is the band. So that's the band that this particle can sit in, right? And this is something they can tune just by dialing up the intensity of the laser. They can tune the hopping, right? The bigger those barriers are, the harder it is to hop and the flatter this band is. Whereas if you want to make this band wider and have the atoms have bigger velocities, you have to tune down the laser so they can tunnel through that barrier easier. Okay. So, but anyways, here's the energy of the band. Now, if I put my force, so my force means I'm adding an additional potential in addition to that one. So I've got this periodic potential, and then I'm just going to add a tilt on it, and the tilt's modest, so it's not changing much from one site to the other. And so we're adding a potential like this. This would be the tilt. I'm adding it to that. But the optical lattice would be going like this on top of that. So we're talking about a much bigger scale. Okay. So now we're going to look at this bigger scale here. So here's the energy. Here's X. And here's this band. right? This is the energy range it's in if I don't have the tilt potential, but the tilt potential tilts it, right? And so it looks like this. And so at each position X, and this is again, we've coarse grained out, and we're looking at it where the spacing in the optical lattice is very small, right? And we're looking on a bigger scale. So here, near this position, I have all possible momenta it could have. So the particle could sit here. Let's not worry about the uncertainty principle right now. So we could put the particle here with any momentum we want. And if it was at the lowest momentum, it would have this energy. If the highest momentum would have that energy, it can sit anywhere in between, right? And that's just, those are just the energies here inside this band. And then if I go over here, all those energies are lower, right? Just because I added a linear potential, which is a constant force, okay? The dynamics, and now we're just gonna, right? So let's say our atom is at this energy, okay? So I draw the line across here. It's gonna move conserving energy, right? And so what it can do is it can sit anywhere along here. So this is where there are states. Up here, there are just no states. And here there's no states. This is below the ground state. This is above the highest energy state. There's really another band way out here, the second band coming from the second state, but it's very far away, and the experiment is such that you just can't get there. Right? So the Bloch oscillation is just the particle bouncing back and forth in here, like this. It's a constant energy. It goes downhill. That allows it to get to higher kinetic energy, lower potential energy, higher kinetic energy, constant total energy, until it gets to the highest possible kinetic energy. Right? And that's different than normal things falling downhill, right? You know, they don't get up to the maximum kinetic energy and bounce back and start going back up the hill, right? But that's what happens with these things, right? You accelerate it down the hill, it gets to the highest possible kinetic energy, and then it starts coming back at you, right? Because of this dispersion relation, right? And that's what a Bloch oscillation is. It just does this. Okay. It's a little counterintuitive, but it happens, and it's, you know, it's easy to set up these ultra cold atom experiments in that regime and see this physics. Any questions about that? So that's sort of okay. I'm gonna now. Okay, so that's just a single atom in this optical lattice. The optical lattice is actually two-dimensional. It's a square lattice. It's this way along this direction. So they tilted along just one direction. And the tilt potential is also an optical field. It's not a standing wave. It's just another laser that's, you know, has an intensity pattern that's roughly linear over some range, right? And it's not interfering with another laser, so it's not making you know, an optical lattice type structure. It's just a single laser.
When you say tilted, you mean the optical lattice itself, or just the added like force?
I just mean you add an additional potential. So you have this optical lattice, which is nominally flat. The reality of the situation is it actually curves up because the lasers are focused, and it's strongest at the focus, and it gets weaker further away. So there's some curvature there, but let's ignore that because, you know, that they can make small. And then they add another light field, which just adds a linear potential which changes the energy. Sort of, it's a much weaker laser than the one making the optical lattice. So it's just putting this gradual gradient on the globe, tilted this way. And so if I added these two potentials, I would just replot that tilted, right? And that's all I mean.
Okay.
Yeah. It's anybody else? Okay. Now, so we're going to put in here now many atoms and tune it so that they scatter with each other and interact. So we're going to start no tilt, hold many atoms. Okay, so now here's my band, and I haven't tilted it. So this is the energy range. This is X. This is the energy range over which there are states. It's cold. What does cold mean? It means it's at low energy. So you're going to have the low energy states, the bottom of the band, low momentum, low energy states, almost filled, and the top of the band, the high energy states, almost empty. They're fermions, so you got Pauli exclusion principle, so you can really only put one electron in each quantum, one atom in each quantum state. And we put a number of atoms in, or they put a number of atoms in, so it doesn't fill up this band. It's half full or less than half full. And so you start off at every position in space, the atoms are, well, it's uniform density for starters. We're going to change that. And the atoms are cold, which means the kinetic energy is low. It's in the lower energy states. The higher energy states are less full. Okay. And then we turn on that other light field. So this is with the optical lattice. That's what made the band. So no tilt with the optical lattice. Now we turn on the tilt. Okay, so what happens when you put something on a hill? It starts going downhill, right? And as it goes downhill, it goes to higher kinetic energy and it warms up. And what happens is very quickly, it heats to infinite temperature. And when I say infinite temperature, what I mean is in this band. So in this band, I have all these states with different momenta, and they're all equally likely to be occupied. They're scattering, the atoms are bouncing off of each other, and they're just randomly occupying all the states with no bias towards high energy or low energy. And that's what infinite temperature is. So it's infinite temperature, but the energy of the atoms is still, 10 to the minus 6 Kelvin, when Kelvin is a unit of energy. Kelvin is also a unit of energy, and the kinetic energy of the atoms is 10 to the minus 6 Kelvin, but they're at infinite temperature, which is kind of funny to think about. Okay. Now, let me just say some stuff about temperature. Okay, so you can really only have infinite temperature if you have a system that has a maximum energy, right? If these weren't particles in a band and you put them on an infinite hill, they just go down forever and go up to arbitrarily high energy, and they wouldn't ever get to infinite temperature. They just get to high temperature, right? So infinite temperature, you need to have a highest energy. And a lot of physical systems don't have that, right? But there are a lot of physical systems that do, like a spin in a magnetic field, right? You can align it with the field or opposite to the field, highest energy, lowest energy, or particles in a band, right? If there's just the states in the band, there's a highest energy state, right? So then you can really have infinite temperature. And when you can have infinite temperature, you can also have negative temperature. So let me just say some things about temperature. And this is basic stuff, but not necessarily something you're familiar with. So the temperature scale starts at 0 temperature, but I'm going to call it 0 plus. So 0 temperature plus epsilon, just above absolute 0. And then you raise the energy, as you raise the temperature, you raise the energy. The middle of the temperature scale is infinity. Infinite temperature is the middle of the temperature scale. And then you go to negative temperature, right? So plus infinity is the same thing as minus infinity. So this is the temperature we're used to. Positive temperature, you go to higher temperature, things are warmer, higher energy. Over here is negative temperature. And this is where higher energy states are more likely to be occupied and lower energy states are less likely to be occupied. It's what they call an inversion, a population inversion. In fact, you set up a negative temperature in some sense in a laser in order to get the atoms in a state where, oh, I got to emit these photons. And then the highest temperature is 0. So the highest temperature is 0, but 0 minus. So temperature plus epsilon and temperature minus epsilon are the farthest apart temperatures. Temperature plus infinity and minus infinity are the same, right? And so the temperature scale wasn't set up in a sensible way, right?
Yeah.
But this is the situation, right? And so this corresponds to the system is in its ground state, and this corresponds to the system is in its highest energy state. And it's just in a random state. Okay. So that's the temperature scale. And again, this part of the scale over here only exists if you have an upper bound on your energy. Then you can go to infinite temperature and beyond to negative temperature. Okay, so what would a negative temperature situation look like? For example, we have this band and it's tilted. If it's at negative temperature, you're going to have more atoms up here and fewer down here. So more atoms here and less atoms here. So the density will be higher at higher energy and lower at lower energy. So this is basically negative temperature. If you're at equilibrium at negative temperature, you have a density gradient on the hill, such that there's more at the top and less at the bottom. And so by measuring so n is the density of atoms, the n of x dx, which they can, so you know, they have these atoms, they're in a microscope, they can actually see them and count them. So they can take a picture of the system and count the number of atoms and look at, you know, are there more here and less here? And so with this, they can measure local temperature. So whenever whenever you're dealing with something, you need and you care about the temperature, you need a thermometer, right? And a lot of times finding a thermometer is hard. But in this situation here, if we're in the right temperature range, they've got a nice thermometer. But you know, they have this tilt. They know the thermodynamic parameters to know how to convert from the density gradient to the temperature. And so just from the pictures they take, seeing the density patterns, they can read off the local temperature. Which often is a real problem in a lot of these experiments, is finding something to know what the temperature is. It's actually a real challenge a lot of the time. Because you can't just dip a thermometer in there. You know, we're talking about a dilute gas that might have 1,000 atoms total, right? Anything you do is going to disturb it, right? So it's actually a real problem a lot of the times in a lot of these cold atom experiments, is finding a thermometer. But in this situation here, they have a very nice thermometer.
Professor?
Can you quickly define temperature again, just because it's not intuitive? Is there a definition that-
Well, the temperature is the the derivative of the total energy with respect to the total entropy.
Oh.
But I don't know if that helps. But you know, I just want to convey it on an intuitive level, which is low temperatures means you're biased towards being in low energy states, or low positive temperatures. You're biased towards to being in low entropy states. Infinite temperature, you're just equally likely to be in all states independent of the energy. And when you're at negative temperature, you're biased to be in higher energy states and less likely to be in low energy states. And then the stronger that bias is, the closer you're getting to zero temperature. That's true on both sides. The stronger the bias is, the closer you are to zero temperature. The weaker the bias is, the closer you are to infinite temperature. Yeah.
So I think you mentioned that if you start with the no to cold atom, and then the energy is just like a horizontal band, and then you add a 2, and then you said that atoms will go down the hill, but because you're adding like just a constant slope, like a constant force field, so that's all the atoms just go to like infinite negative energy.
No, because there is no infinite negative. Oh, yeah. So first, yeah, the energy is conserved, right? This is a closed system. Energy is conserved. A single particle won't go down the hill. It'll bounce back and forth, right? So the atoms, they all initially, because they're cold, they start downhill. And then they start doing block oscillations and bouncing off of each other, but energy is conserved, right? So there's no net flow down the hill because that would violate energy conservation.
So why do we need like a highest energy state to get infinite temperature?
Well, if there wasn't a highest energy state, they would do what you expect, is they just fall down the hill and accelerate up to very high kinetic energy, right?
But shouldn't you need like a lowest energy state for them? No.
Well, if they weren't in a band, right? If it's just freshman physics and you have an infinite hill and you put the ball and start it rolling, it just accelerates forever, until it gets to the speed of light, right? Because there's no maximum to the kinetic energy, right? So what's special here is the kinetic energy is bounded. It has a minimum, it has a maximum. So even though the potential energy is unbounded, if I let this go on, so if I let this go on forever, the potential energy is unbounded. But because the kinetic energy is bounded, they can't fall far down the hill because it would violate energy conservation. There's no place to put that energy, right? And as soon as if the temperature is positive, they're biased to go down the hill because what they want to do, they don't care, energy is conserved. What the system does, when you have a system like this, everything's scattering off of each other, what it wants to do is maximize the entropy, right? And the entropy is maximal at infinite temperature, right? Entropy at infinite temperature, everything is equally likely. That's the maximum entropy. So if the temperature is positive, things fall down the hill. If the temperature is negative, they fall up the hill because by going up the hill and converting some of the, if your temperature is negative, it means you've got too much kinetic energy. And by going up the hill, you can convert some of that kinetic energy to potential energy and get the kinetic energy to infinite temperature, which maximizes the entropy. Because the entropy is everything bouncing around. It's really in the kinetic energy, right? So it's very counterintuitive, and that's why I wanted to tell you guys about it. And it was, this isn't what we were trying to do when we, my student Alan, when he proposed them to do this experiment, this is not what they were trying to do. So, they got some data. We had to figure out what the heck was going on because it wasn't what Alan had in mind. They didn't even ask me. It's actually a nice story. Alan had this idea. He knew the guys in Bakker's lab. And he said, oh, why don't you try this experiment? And they said, you know what? We could do that just in a couple days without even asking Professor Bacher, because if we ask him, he'll tell us not to do it. So they just went ahead and did it without asking. So nobody asked any professors, but they got some beautiful data, right? And then the professors were interested, which is, it's kind of an unusual thing. But these experiments have this flexibility where you can actually set up and do a new experiment rather quickly once you spend 2 years building the lab. But once you know how to operate all that equipment, you can actually change things around and do something different rather quickly. And we were able to take advantage of that. So let me just try to get to. Okay, so what? Yeah. So now we're gonna put on yet another potential. So we're gonna put on another potential. Let me draw it over here. So here's my band. And now I'm gonna put on a sinusoidal potential in space with some wavelength unrelated to the optical lattice and the light, like this, and fill this with cold atoms, and then we'll get a higher density here and a lower density here. So we'll be able to prepare a state with a non-uniform density with some periodicity to the density pattern, okay? And that looks like this. So this is now n of x versus x, and it is oscillating with some wavelength. And this wavelength is long. Was typically what they put on might be 4 to 20 times the optical lattice spacing, in kind of that range for the wavelength. Okay, so this is versus x. So this they know how to prepare. So they just put, they have a projector that's like that, but it's much fancier, and they can just project whatever pattern of light they want onto their experiment. But it's basically one of those. But, a nice one. So they can put on whatever potentials they want, but they can put this on and then cool into there. It's not tilted. It won't heat up to infinite temperature. It'll cool down and put a higher density here and a lower density here. Right? So that's a nice initial state with this non-uniform initial condition. Okay. And now so first you do that. Now you add the tilt. This whole thing slides down the hill a little bit to get enough potential to get enough energy from the potential energy to heat the whole thing up to an average temperature that's infinity. An average energy that corresponds to infinite temperature, right? Which is right. And now this is uphill, and this is down. Okay. So here, this is positive temperature, right? When you're at positive temperature, the lower energy stuff has more probable and the higher energy stuff less probable, right? Because these are lower down the hill, so this is lower energy than this, right? So the positive temperature here, negative temperature here, positive temperature here, etc. So by preparing this, they can set up this situation with this pattern of density, non-uniform temperature. They can measure both the density and the temperature. Okay. And the falling down the hill and heating up happens very quick. They're putting tilts on that are big enough so that that's just so fast. I don't know that I'm not sure they really measured that, but that's not the time scale they were following. Okay, so now remember, this is again counterintuitive. The negative temperature is higher energy, higher temperature than the positive temperature, right? Because the temperature scale was defined in a messed up way, right? So this is hotter, this is colder, right? And this is going to set up heat currents. So this is now the heat currents. Heat flows from hot to cold, and it flows from negative temperature to positive temperature because negative temperature is hotter than positive temperature. Right? just because the temperature scale is. So you get this oscillating pattern of heat currents flowing like that. And the heat flowing out of the negative temperature region will cool it down. And so it'll become, again, it's counterintuitive, become more negative, closer to minus infinity, which is cooling down. And the heat flowing into the positive temperature region will heat it up, and it'll heat up towards positive infinity. Okay, but because the temperature is proportional to the gradient of the density, if this is going to cool down, this gradient has to get smaller, and if this is going to heat up, this gradient has to get smaller. So associated with this is a mass current or an atom current. So this situation, you get an atom current, which is flowing from high density to low density. It's the system is trying to go to maximum entropy, and obviously the maximum entropy is going to be where the density is uniform, and the temperature is infinity, right? And so the atom current's going to flow like this. Whoops, I'll draw next to the atom current here. So this flows downhill. Right? And now, like here, the heat current coming into this positive temperature region is trying to heat it up. But as a consequence of that, this gradient gets smaller and the atoms move uphill. And so almost all this heat goes into just moving the atoms up the hill. So, usually if you have a non-uniform temperature and heat flows, you get the diffusion equation, and the relaxation time of such a pattern would go, the time to relax, let's say this distance is d. The time for this whole thing to relax away would go as the diffusion constant times the length squared. That's diffusion. But here, the heat flows, and it doesn't actually succeed in raising the kinetic energy of these atoms very much. Almost all the heat goes into potential energy of the atoms that, because this heats up, this gradient has to decrease and the atoms go up the hill. And so it's not like standard diffusion. The heat is diffusing, but it's not heating the system up. It's going into all this potential energy. And so because of this, and I can go through the math of that, but I don't think I should, you end up with the time scale for this whole pattern to relax to equilibrium going as the thermal, so this is the thermal diffusivity, the rate at which heat diffuses, but it ends up going as the distance, to the fourth. And this is what we call subdiffusive transport, because it's much slower, right? We do a longer length scale. Instead of the time going as length scale squared, it's going as length scale to the fourth. It's slower by 2 powers of the length. And this, they could do this over a factor of 5 roughly in d, so this time scale changed by a substantial amount, and so they're able to see that, which and you can look at the paper which I mentioned to see some more of that. But that's at least the basics of the story. You can write out the equations to see how this all works, but I think that's probably not appropriate at 5:20 in the afternoon. Yeah.
Can you repeat again why temperature will the local temperature?
Let's think. What's a good way to say that? Well, the temperature is measuring, sorry, this formula is bad. 1 over the temperature. Is that what you were worried about? Probably not. Right, because of course at infinite temperature, there's no gradient. Right, and so this should have been 1 over the temperature. But the temperature, when it's positive, well, the temperature is 1 over the temperature, is telling you how much is the population at equilibrium at that temperature biased towards higher energy or lower energy, right? And so since the gradient with respect to x is this way, and the band tilts down, so the gradient with respect to x is really a derivative with respect to energy, right? And so this is a measure of how much the local population is biased to either be uphill or downhill. Right? And that's what the temperature does, is it's a bias between it's a bias between high energy and low energy. And it can have either sign if again you have an upper limit on the energy, right? If you give negative temperature and you have no upper limit on the energy will just go up to infinity, right? And so that's why the upper limit's important. I don't know, that's sort of a casual answer to your question, but is that good enough for now? Yeah. Anybody else? Yeah, that's basically what I wanted to say. I wanted to, sort of show you, there's a whole bunch of kind of counterintuitive stuff here. This whole story, it's actually pretty basic. It could have been worked out long before we did it, but, they actually got the experimental results and we had to figure it out for ourselves. And it was a lot of fun.
Well, thank you so much, Professor.
Okay. If anybody wants to ask, anything broader, about a professor's life or whatever, go ahead.
Yeah.
I did want to ask if you had any advice for someone that wants to be involved in AML research, because this is something that I'm really considering doing, but as a first year, like without having taken quantum, it's obviously difficult to get started on it. But if you had any advice to get started on it early.
Professor Bacher, Professor Chook, Professor Thompson, a bunch of people up in the electrical, just approach some of them. You don't, in the laboratory, there's work for freshmen, right? Right. You don't need to know quantum mechanics well to do a lot of the stuff that needs doing, and then you get around it. You get around it, you sort of see it, and yeah.
So the unrelated question, but is it possible that the intertopology of some particular type of metal amalgamation can change like inter aspect of like superconductivity of like material? There's like this one particular material, I'm like talking about like molybdenum ditelluride, that like if you take like a monolayer of like the material, it suddenly becomes like superconducting. And also like, is it possible to like explain like theoretically?
Probably. This is not something I'm keeping up with, so I'm not the right person to ask about that. But yeah, it's amazing what people are doing these days with these single layers of crystals and stacking them up and getting them to do all sorts of different things. It's a very rich topic, but it's not one I keep up with, so I can't really address that.
Yeah, sounds good. If you have any other questions, you can talk to Professor Huse if he has any, like some additional time. But for now,
I can hang around.
yeah, there's boba, and we could start to distribute that, I guess. Yes. Thank you so much for coming, everyone. And yeah.
Thanks for organizing.
Yeah.
Okay, great.
Would you like boba?
It's all the same?
Yeah, I would assume so, yeah.
Okay, I'll try one.
Yeah.
I'm the CEO, yeah, right now, but. Oh, no, go ahead.
Here you go, Professor. Thank you so much for the thoughts. It was really helpful. And I think some people were really. Get it. Oh, I think you just have to.
Oh, it's a
Yeah,
bubble.
you could just, yeah.
It's a bubble.
Yeah, yeah, yeah.
Bubble.
Yeah. Oh, wait, how do we, okay. I stopped the recording. I just need, I can't read. Don't